omnidirectional LiDAR using a single-point LiDAR sensor. Hi, I'm Arnav, and in this project I created an omnidirectional LiDAR using a time-of-flight TF Luna sensors, LEGO turntables, and motors, all working together with the Raspberry Pi and the Raspberry Pi built-out. Let's dive into what that means and what this project is all about. Start by talking about what a LiDAR actually is. LiDAR stands for light detection and ranging. LiDAR sensors shoot out laser pulses to measure distances. Our LiDAR will be omnidirectional, which means that it will be taking measurements at different angles. Alright, now it's time to talk about the different parts of the robot. Let's start off by talking about the TF Luna, which is seen right here on this piece of acrylic, a type of plastic. The TF Luna is a single-point time-of-flight sensor. What is a time-of-flight sensor, you may ask? It's exactly as it sounds. A time-of-flight sensor measures the time it takes for a modulated laser pulse to return from hitting an object. It's a version of echolocation that uses light instead of sound. However, the TF Luna is single-point, and we need an omnidirectional LiDAR. The solution? LEGO turntables. We have two of them, which are here and here. And because we have two turntables, we can now take scans in 3 dimensions. Now that we are rotating, we need to account for the angle that a measurement is taken at. The data output advertised by LEGO for their motors is 100 Hz, but I'm only receiving 2 Hz because of the latency in the build-out. More on that later. To solve this issue, I assume a constant angular velocity and timestamp every 360 degrees. For this timestamp, I use an IR brake beam sensor, which is located at the back of the robot. The IR brake beam sensor will identify when the beam between the 2 pegs is broken and record the time at which it was broken. And we will see the LEGO piece that will actually break the sensor in a different picture. So not only do we need to identify rotation, but we need to prevent our wires from tangling up from the rotation. To do this, I use 2 slip rings, one of which can be seen right here. So slip rings are used to prevent wires from tangling during rotation by only rotating a small ring within the actual slip ring. The wire will remain stationary. Our robot is also equipped with a camera, which can be used in the future for localization and simultaneous localization and mapping. There's also a battery pack in the robot down here for when the robot is not hooked up to power. Alright, so now let's take a look at the modular robot base. As you can see, the TF Luna will fit very snugly at the back of the robot right here. This angle also permits us to get a better angle of the camera, again, where you can see the Raspberry Pi camera. And we also see another major component, which is the build hat. So the build hat is used to connect to LEGO motors and sensors through these 4 ports. So HAT stands for hardware at top, and it quite literally is on top of the Raspberry Pi, which is right below. The build hat is allowing me to rotate the turntable and move the motors through the Raspberry Pi UI. Alright, so now let's look at the TF Luna disconnected from the modular base. So anything from the blue plate and under actually connects to the modular base. And here we see another angle of the slip ring right here. And this is actually the LEGO piece that will break the beam in the IR brake beam sensor. We also see one more important part of the robot here. This is the USB to serial over UART communication right over here. And this allows the TF Luna to connect to the Raspberry Pi, and I can control it from there. Let's have a look at the 3D motion in action. As you can see, both the turntables are working simultaneously with no snags on the wires. So the 3D LiDAR is hardware ready. This is a series of 2D scans taken from the TF Luna LiDAR placed at the center of this enclosure. Alright, let's have a quick look at the 2D scan data recorded from the TF Luna LiDAR. So, the data starts off by showing us the start time and the stop time of the data in seconds. These increasing numbers each represent a scan, and each of these scans have their own measurements. At the bottom, we also can see some overall statistics. For example, in this specific test run, our mean was 0.78 Hz for scan rate, and our sample rate average was 48 samples per second. Alright, continuing on with analyzing the data, let's have a look at the sample rate setting versus the sample rate itself. So the trend is linear for the first 50%, where it peaks at 48 samples per second. I'm currently researching why it saturates at this value, considering how it was advertised to go up till 250 Hz. Next, let's look at the motor speed setting versus the turntable speed itself. Again, it's linear, this time until 80%. However, the value at 80% is still a reasonable value, considering the 3-to-1 gear reduction ratio. The max expected is, without load, 60 rotations per minute, so 48 rotations per minute at 80% is a reasonable value. This is the characterization of the accuracy of the TF Luna ladder. In the left graph, we see a polar plot of the accuracy chart, and on the right, we see the error on another polar plot. So from this, we can see that the error is a few centimeters, and it especially spikes at the corners of the enclosure. This is the main module for the TF Luna ladder. It generates 2D scans for a specified sample rate and the speed of the Z-axis motor. It uses the TF Luna library from Maker Portal and the Raspberry Pi's BuildHat library. Here I'm initializing the variables and setting the GPIO pins. Initially, I tried using the built-in functions for getting motor data from the BuildHat, but the BuildHat had latency issues which needed to be resolved, so I relied on the IR breakbeam sensor. This function is the interrupt handler and updates time and scan numbers when the beam is broken. We are setting the interrupt to happen at the rising edge here. This next function sets the TF Luna at 0 azimuth. This final function generates the scan. You keep recording the scan until the beam gets broken. This script is used to acquire and display ladder data. Some of the code is based on an Adafruit library. We set the port number, speed, and sample rate. We set up a Pygame window and fill it with black pixels. The process data function takes the ladder data and converts it into Cartesian coordinates. The XY coordinates of the pixels are then turned white. We then set up a TF Luna generator and an array to store a scan. We get a scan and parse it. The angle is computed assuming uniform angular velocity and the time elapsed from the start of the scan. This script is used to generate scan rate and sample rate statistics. The TF Luna generator is set and 100 measurements are obtained. Averages are then computed and displayed. And that concludes what I did this year. However, I've created a robot and now it'll be time to test it. So as you can see, I'm standing in this room with this massive test bed. In this test bed, I'll be conducting localization and simultaneous localization and mapping, what I plan on doing in the future. I hope to be back next year to present my findings.